Okay, so since we started the recording, we'll be covering computational complexity in this recording, and then we'll cover the remaining material in a separate recording that you can watch. So anything like, you looked at kMeans, there is a computational complexity for that. There's convolution, there's computational complexity for that. Matrix multiplication, there's computational complexity for that. So any algorithm method that we've covered so far or we'll cover has a computational complexity. And it's important to be able to say what the computational complexity is. Like this is something that will come up in an interview too. Like you go for a, data science, machine learning engineer, or applied scientist, or whatever software engineering interviews, right? They might ask you a question on coding, and then they'll say, what's the computational complexity of this method that you just came up with? And so today we'll cover that in the context of whatever algorithms we've looked at so far. Are people familiar with this concept? Like maybe from a different course? Show of hands. Okay, I see 1, 2, 3, 4. Okay, good. Yeah, but it's even if you're familiar with it, since you're looking at matrices, there may be some new elements that come up as we go through it. Okay, so this is the interview favorite question, like I mentioned, and there's also space complexity. So people will also ask you, what's the space complexity of the algorithm that you came up with? So computational complexity and space complexity, these are two questions. Like invariably, any interview that involves coding to whatever extent will have this. So becoming familiar with this and being able to talk about the complexity of the algorithms will be something that would be expected of you, right? Oh, you got the lecture slides, Ayush?
Yes, I've got it. I removed some of the last end of the slide, so yeah, I'll just make a few more amendments and share in a few minutes.
Okay, great. That's awesome. Maybe just send an email and then I can get started with that.
Sure.
Yeah. All right. So thanks to Ayush for that workaround. Okay. So yeah, let's look at an example. So very simple example. So let's say we want to add n numbers and output the result. What's the computational complexity here? This should be very simple. N, right? So you would say it's O of n. The O is order. So it's on the order of n operations. It's not telling you what the time is. The time might be whatever, depends on your machine, right? If you're using a really fast machine, you might take much less time. If you're using a slower machine, it might take more time. But if you fix all the hardware, right? I'm using this machine, I'm using these many CPUs, or I'm using this kind of a threading. You fix all of that, then ON would look different from ON square. ON square on that fixed machine is going to take more time than ON is going to take more time than O1, right? So why is it ON? I mean, let's say you have 1 plus 2 plus 4 plus so on plus something 100, and this is n numbers. Well, you have to add 1 to 2, then you have to add 2 to this, 4, add 4 to this. So each of this is O1 because it's one operation you're adding. Even if you replaced addition with multiplication, that's still one operation. You subtract, that's still one operation. So that's O1. But then you're doing O1 n times. So that it gives you ON. Yeah. So it doesn't matter what the numbers are here, right? you could have any numbers in between. On minus 1. Yeah. So
Yeah, because you said for 1 plus 2 is 1. So I was thinking.
Yeah. So On minus 1 is still On because it's on the order of n, right? If you had square root n, then you would not say that's on the order of n. You would say that's on the order of square root n. Yeah. If you had O2n, right, is still On because this is a constant. So we're not saying, so you might have two algorithms that take On, but one is always faster than the other. But that's faster in a constant time. It's not faster on the order, right? So it might take 10 seconds faster, but that doesn't mean the order is different. It could mean the order is different, but it doesn't have to be that the order is different. Okay, so this you would say is On. Yeah. Let's look at another example. Okay, let's say you have a matrix. So since we've been talking about matrices, and let's look at the diagonal entries here. Okay, and let's say this is an n by n matrix. Okay, so here's a question. You want to sum up, sorry, not sum up. You want to multiply all the diagonals in X. Okay, so what would you say is the computational complexity here? On square. Okay. On. Okay. So how many elements are we looking at? We're looking at n elements, right? The matrix has n square elements, but we are only picking the diagonals. So you don't have to worry about the rest of the elements in the matrix. And you're multiplying them. Well, each multiplication is one operation. And you have to multiply it, n minus 1 times or n times. It's the same thing. So that is still On, right? Yeah. Okay, that's nice. Let's look at a third example. I don't know if this was part of in-class exercise. No, I don't think this was part of in-class exercise. Okay. All right. So let's say you have two images, I1 and I2. Okay. So these look like this, like matrices. But now what you did is you apply tSNE to it. Okay. So tSNE gives you an embedding, right? So you got embeddings for these two images. So let's say the first embedding is U1 and the second embedding is U2, and both of them are in Rn. So maybe this is some m by m image pixels, but then your embedding got reduced to n dimensions. So U1 and U2 are now vectors. So I1 and I2 are images, but U1 and U2 are embeddings and they are vectors. And we spoke about the concept of embedding last time, right? Embedding is a more concise representation of an image or an object that has just enough information that you can do something with it. For instance, image search or image chaining, like we are doing in the assignment 2. We're taking images and chaining them to make it into a video. So that's an application. Okay. All right. Yeah. So that's an application, right? So now maybe I want to look at if U1 and U2 are similar or dissimilar. So here's U1, U2, and maybe we have something else, U3. So this is in two dimensions, right? So here we are able to visualize U1 and U2 because they're in 2 dimensions. In higher dimensions, you cannot visualize, but you can maybe understand how it looks like. In 3 dimensions, again, you can visualize, but you cannot visualize more than 3. So that's why our examples are always going to be in 2 dimensions, but you have to extrapolate it to whatever n dimensions, 100 dimensions. So here I want to also mention the concept of similarity. So how do you say 2 images are similar if you're given their embeddings? Right? What would be an operation you can do on U1 and U2 that can tell you if they are similar or dissimilar? Any thoughts, anyone? Dot product, yep. So similarity is measured through dot product. But if you want to be more normalized, you can say cosine similarity is a more accurate way to measure similarity between 2 vectors. So cosine similarity is nothing but the dot product of 2 vectors, but normalized for their normalized by the magnitude. It also turns out cosine similarity is the angle between U1 and U2. Okay, so this angle here is the cosine similarity. Cosine similarity, yeah, so this is the cosine of this angle, cosine of the angle is a cosine similarity between U1 and U2. So when is the cosine of an angle the maximum? At what angle is the cosine of an angle the highest? When it's 0, right? Because cosine 0 is 1 and cosine 90 is 0. So when the angle is 0, the cosine of that angle is 1. That is the highest you can get for cosine similarity, which makes sense, right? If theta is 0, then U1 and U2 just collapse. If they collapse, they are the most similar, isn't it? But U1 and U3, maybe this angle is 90 degrees, right? So the cosine similarity here, so U1 dot U3 is going to be 0. Yeah, so you would say U1 and U3 are not related, but U1 and U2 are very much related. The smaller the angle, the higher the cosine similarity and the more similar they are. So this is how, you have these complex images or complex objects in high dimensional space, but then you use something like tSNE or SVD to get a low dimensional embedding. So maybe here n is like 100 or 500 or something, lower dimensional embedding. Now these embeddings, you can almost visualize it because here we're in 2 dimensions, you can almost visualize it. You kind of put them here, okay, U1 is here, U2 is here, U3 is here. Then you ask, is image 1 similar to image 2? Well, look at the cosine similarity between the U1 of image 1 and U2 corresponding to image 2. If that is high or if the angle is small, then they are similar. Yeah, so this is how embeddings are very helpful in understanding how things are similar or not. Yeah. So here's a question for you. I want to understand why dot product or cosine is better than other measures like. Yeah, I don't see how t-SNE. Okay, so there is a couple of questions that was asked here. So why is cosine similarity a better measure than other measures, right? So let me put that back to you. Why would you think cosine similarity is useful as compared to just dot product, as compared to maybe Euclidean distance? Well, for one, it is normalized. You can have a U1 vector that's really long and U2 vector that's short, but if all you care about is do they fall in the same space, then a Euclidean distance would give you a different answer for different lengths of the vector. So it has been shown that for certain kinds of data, like documents or images, cosine similarity make a lot of sense once you have a good representation for these vectors. Yeah, because it's normalized. So this normalization, so even if you scale, so here's an example. Cosine of U1, U2, this cosine similarity is the same as cosine of alpha U1, U2. Do you guys agree? So what is cosine of alpha U1, U2? It's alpha U1 dot U2 divided by the Euclidean norm of alpha U1, U2. Oh, but look at this. The alpha here cancels out. So you get U1 dot U2 divided by the magnitude of this. And this is the same as cosine of U1, U2. So cosine similarity is invariant to scaling. If that is a property you would like to have in understanding similarity between objects, and here, this is where you have to look at the data space. For certain kinds of data, that is more preferable than having scaled versions of this. Then it's a better measure for similarity. Yeah. Okay, and the second question that was asked is, how is it connected to tSNE? Well, if you just use raw images and compute cosine similarity, there could be noise in the images. There could be artifacts that are, that are not as relevant. And also, you may not take in the full context of all the other images that are present in the data set, right? If you just take the cosine similarity between I1 and I2, that's just between I1 and I2. But U1 and U2 is not just learned from I1 and I2, it's also learned from many other things. Yeah. So it's also looking at the whole space and then embedding it. So usually embeddings have more concise and better representations than the original object itself. So for that reason, you would want to take an embedding and then apply cosine similarity, because you have factored out noise, you've factored out overfitting, you've taken the overall context into account, and it's also faster. Did I mention faster? It can be order of magnitudes faster, right? If you have 1,000 by 1,000, that's 1,000,000 pixels. But if you have 1,000 dimension representation, that's 3 orders of magnitude faster. Yeah. So of course. So you don't want to lose information. So it doesn't mean you make n to be 1 or 2. If you only have 1 or 2 dimensions, what are you going to know about an image? You may not know, you may not capture enough information. So n has to be sufficiently large. That's the key thing in any of these embeddings. You can't make n to be 10 or 20 and then expect to have enough information about an image that you can actually compare them. Yeah. So here we have two concepts. One is embeddings, and then the other is similarity between objects, right? So and we're kind of combining them. Okay, so now that you've spoken about cosine similarity, my question is, it's obvious. What's the computational complexity of cosine similarity of vectors in Rn? So to do this, you have to look at all the operations involved in the cosine similarity. So go back to this definition here. There is U1 dot U2. There is normalizing U1. There's normalizing U2. And there is dividing everything else, dividing the numerator by the denominator. So you have to combine all of that and then see what is your complexity. So ON, does ON make sense? Yeah. I mean, it's not too hard. Like we said, so what is U1 dot U2? The complexity for this ON. Yeah. You take each element in U1, each element in U2, multiply it, that's O1. You're doing it n times and adding it, all of that is still ON. Yeah. It might be 2n, 3n, whatever, but 3n is still ON. Okay. The Euclidean norm of U1 is, what's the complexity here? ON, right? Because you're squaring every element in U1, summing it up and taking a square root. Square root is O1 because you've already computed some number. Squaring is O1, but adding the elements is ON. So that gives you ON. Okay, so the same thing for this as well. So if you have ON, 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 it's going to add up. It's not going to multiply because you have three separate operations. So ON plus ON plus ON is still ON. But ON plus ON plus ON n times is ON squared. So that's where you have to see how many times are you adding things, right? For matrices, you might get, oh, I'm doing this ON, but I'm actually doing it n times. So that becomes ON squared. But here we're only doing it 3 times or 4 times. So that's still ON. Okay. All right. Just going to pause recording here. Recording. Okay. All right. So computational complexity. Yeah, so O1 is better. So O1 is less than ON is less than ON squared. So you always want to see if you can go this way, right, for any algorithm. I mean, you can even have O n log n or something in between, and that's still obviously better. So n log n is better than n squared. Okay, so we covered some of the diagonal entries of the matrix. Yeah, so one thing I want to mention is summing up the diagonal entries of the matrix. This is O of n. Multiplying all the elements in the same matrix, that's ON squared, right? All the elements, not just the diagonal. Okay, so so we say that summing up the diagonal entries of the matrix is faster than multiplying all the elements in the same matrix. However, when you actually go to Python and you say, let's set n equals 2, okay, let me just test it out. You might not notice any difference in the time taken. That's because of constants or loading the matrices and other operations that happen. But make n equals 10k and suddenly you'll see the ON versus ON squared starts to show up. And one might take 10 seconds and the other might take like 1 minute. So suddenly you start to notice a difference. So on the order means, yes, as you keep increasing n, you're going to see a big difference. But if your n is really small, it may not matter. Like if n was 1, then it's the same thing. You will not see any difference. But for large enough n, you're going to see a difference between the two. Yeah. Okay, so we looked at dot product and or inner product of tSNE embeddings and the computational complexity for that. Yeah. Okay. So summing up n integers has the same computational complexity as a dot product of 2 tSNE embeddings of dimension n. So we looked at that. Both of them is ON, right? But does this mean the runtime would be the same as well for both these operations? No, right? We just discussed that. In fact, the runtime is going to be almost always higher for the tSNE embeddings as compared to the summing up n integers, because there's just n operations exactly, you're just adding n things. But the tSNE, you have to do it multiple times. You take the dot product, multiply 2 things and then add them up. So runtime is always going to be higher, but it'll be in the same order. So if one takes 100 seconds, the other will take 120 seconds. If one takes 10 seconds, the other will take like 11 seconds. So you'll be on the same order. Okay. Right. So let's actually look at an in-class exercise. So we can use all the things we've looked at, all the examples we've looked at so far on computational complexity to answer this question. Yeah. And this could even be an interview question. So, things like this do show up in interviews. So just kind of pay attention and see what is coming up for you. Yeah. So I see ones and twos. It seems like two, but it's actually one. Yeah. Okay. So how do you see that? Well, again, always helps to visualize things in these kind of questions. So your utility looks like this. That's m by k. K is smaller, so it looks like a taller matrix than wide. And then v tilde looks like this, k by n. Okay. So the easiest way to do it is pick just the first column here, and then the matrix here. This is like, so this is m by k, and this is k by 1, right? So you just have one column. And then just take the first row here. So what is the complexity of multiplying the first row with the first column of v tilde? That's k. How many rows do we have? M. So that's mk. So it takes mk to multiply this with this. How many columns do we have in v tilde? N. So that's mk n. Yeah. It's not it's not mk squared n. So that's how you are able to compute the precise complexity for matrix multiplication in this case. Okay, second question. We've looked at convolution before, so I thought this might be a good example as well to understand deeper the complexity here. So again, take a minute or so to work on this. I see I'm not recording. Okay. So I had a couple of questions after lecture on kMeans, computational complexity. So I thought I would cover it here. So let's say we have three clusters, cluster 1, cluster 2, and cluster 3. So here you have to make an assumption. Okay, what's the assumption? Well, let's say there are n data points and k clusters. So the assumption is the clusters are balanced. So balanced clusters mean there's roughly the same number of data points within any given cluster. So there are k clusters and n data points. There's going to be roughly n over k data points per cluster. Yeah, that makes sense. So this is n over k, and then n over k. So then you have to just look at the kMeans algorithm. What is kMeans doing? Well, in one of the operations, it's averaging all the points in a cluster to find the new centroid, right? So if you have a d-dimensional vector here, and you're taking average of n over k vectors, so the averaging is going to be n over k times d, right? For one cluster. But then you're doing it for k clusters. So that's going to be multiplied by k. And then the other is assignment. You assign every point to a centroid. Let's say you computed these centroids, you need to again assign the points to the centroid, right? And then see if they stay the same or not. So that assignment, for every point, I'm going to compare it against k centroids. Comparing a point against one centroid is order d. Comparing it against k centroids is order kd. And I'm doing it for n data points. So that's order n k d. Okay. So what do we get here? Assignment is order n k d, and averaging is order n d. So obviously assignment takes higher complexity than averaging, So order ND plus order NKD is still order NKD. Do you guys agree? Because it gets subsumed in it. And then the number of times you have to go through kMeans. Assuming that you go through the kMeans iteration, constant number of times, you're multiplying order NKD by a constant, which is still order NKD. So this tells us that the computational complexity of kMeans equals order NKD. And this analysis assumes you have balanced clusters. So this is how you can take any algorithm, break it down, make a couple of assumptions. For example, here we made assumption that it's a balanced cluster, and then do your analysis and come up with a rough approximation, or it could be exact, for the computational complexity of that algorithm. And that tells you, is it faster or slower, right? As compared to some other algorithm. So if you came up with, if you're doing research in machine learning or data science or whatever, signal processing, and you came up with a better algorithm, you say, my algorithm is better, it's faster, you have to show that your complexity is somewhere better than an existing method. And then you can claim it's faster. But sometimes people also say, well, the constants do matter. In some cases, maybe at a billion scale, a constant matters. You're still saving time. You have a latency limit. At that time, you might still want to optimize for constants as well. So that can also happen in an industry setting. People say, hey, just optimize as much as you can, even the constants. But for understanding purposes, we don't worry about constants so much. But in practice, you might, depending on the application, you might worry about the constants too. Okay. Yeah, so what was your question? For which step, assignment or averaging?
The final is the computational complexity you liked. I'm kind of confused.
Yeah. So the final complexity is, so number of iterations of kMeans times complexity in one iteration. Do you agree? This is like high level, this is the breakdown. So now let's look at this part. So this is complexity for averaging plus complexity for assignment. Do you agree? So this is order ND, which we just computed, plus order NKD. Okay. So if you actually add it up, it's order ND k plus 1, which is still order NKD. Yeah.
Thank you, Gotcha.
Okay. All right. So yeah, we spoke about this. So when you say an algorithm is faster than some other algorithm, so A2 is faster than A1, if the order of A2 is strictly less than order of A1. So this is like how you would compare algorithms, right? So if suppose I asked you, which is faster, selection sort or merge sort, what would you say? So for that, you need to know the complexity of these algorithms, right? So the complexity of selection sort is usually n squared, and merge sort is n log n. So this log n is obviously less than n. It could have been square root n too, and you would still say it's faster, but log n is much faster than n. Like when n is like a billion scale, I mean, you'll see a very big difference between selection sort and merge sort. Okay. Right. Okay, so let's move on to the next topic for today. We were talking about data visualization, and we spoke about the tSNE algorithm last time. And we said, a motivation is like, let's say you had 1,000 images and you wanted to chain them, or you want to arrange them in a super grid. How would you do that? So yeah, I don't have the visual here, but we looked at that visual, right? With images placed in every single row and column. And stochastic neighborhood embeddings and a variation of that, tSNE, is a way to do very good data visualization. Yeah, so the high level idea for SNE is find an embedding of images in some dimension. It can be 2 dimensions or even higher, so that similar images are close to each other and dissimilar images are far away from each other, right? And here a couple of things I want to mention is tSNE gives you a probability of picking the next image J given an image I that's given in this fashion, right? So this allows you to use the probabilities for chaining. So let's say I'm at an image I want to pick the next image. What does the next image look like? Then I can just basically look at the probability of next image given I. If this is high, then maybe you can chain it. If this is low, then don't pick it. So you can actually use this as a probability distribution to pick the next image. Yeah. So we spoke about this last time. And we also did a breakout where we spent some time looking at how you would do this. I think a couple of things that came out of the breakout last time is this obviously gives you a straightforward algorithm, right? One is start with any random image and then use this probability distribution to pick the next image, which has a high probability. It doesn't have to be the next image that has the highest probability, but it could be a next image that has a high enough probability, so which is called sampling. You can either sample from the probability distribution, or you can pick the best, the next image that has the best probability in this Q distribution. So both are, you can experiment with both for assignment 2 and see how it changes your video, right? So sometimes it helps to sample from a probability distribution, then pick the best image, because you might be biasing the model. There may be biases that are introduced. Also, if you want, it depends on your application. You want some amount of uncertainty, or you want to average for any bias, then it helps to keep the uncertainty on, right? Versus keeping it very uncertain and then picking the next best image. In the context of videos and chaining images for videos, you want to do any of this so that you get a smooth transition between images, right? If you look at any video that has all these transition of images, usually there is like a nice change from one set of images to the other set of images. So whatever you do here, you're trying to get there. Like you're trying to do your operation so that you can get a smooth transition between different set of images when you build your video. Yeah. Another idea that came up in the breakout is maybe we can do clustering beforehand and then use the clusters to inform your chaining. So if your clustering is giving you a cohesive set of images within each cluster, then you can walk in a given cluster and then go to the next cluster and then go to the next cluster and then chain them all at the very end. So that's one idea. And this is only if direct chaining is giving you weird results for whatever reason. Maybe you're at the edge of a cluster, you went from one cluster to the other, but you didn't finish the images in one cluster. So you'll have to come back. So I was going through roses and then suddenly I jumped to jasmine, but then I had to go back to roses again. Why didn't you finish the roses in the first place? So that when you ask that question, then I would say, okay, maybe do clustering, and maybe the roses are captured in a different cluster, and then you can walk through the roses and then walk through the jasmines and walk through something else. Does that make sense? So depends on how the chaining is happening. So you have a lot of room to experiment with these ideas for your assignment too, and see which one gives you a good transition for the video. Yeah. Also, you have room to experiment with the dimension of the embedded vector. So your embedding can be in different dimensions, 2 dimensions, 4 dimensions. It doesn't have to be in 2 dimensions. 2 dimensions gives you a location, but doesn't have to be in 2 dimensions, because you can still, you're just chaining, right? So you just need a probability. So maybe even higher dimensions than 2 can give you a better representation for an image, which can help you do better. So you may have to experiment with the dimension as well in your tSNE embeddings and see which one gives you a good representation that when you chain it, it looks good. So those are some things that you may have to experiment with in your assignment. Okay, any questions on this before we move on? Okay, all right. So our next topic for today, which is also part of assignment 2, is total variation for image smoothing. So we'll be looking at new set of methods or algorithms that can help us with smoothing an image, denoising an image, making an image look better than where it was. So a lot of in computer vision, a lot of images can sometimes suffer from noise for whatever reason. There's like low light condition, the resolution wasn't good, but you still have to work with that data. So if you can make it better, remove the noise, and then do your machine learning or computer vision, you will get better results. So this is an important pre-processing step, you can say, before you start applying machine learning to images. Or it can be an end application for you as well. You just want to denoise images. You just want better images. Either way, you may want to do something like total variation for smoothing images and denoising. Let's take like a 3 or 4 minute break, and we'll come back. I'll also work on some of my slides, and then we'll come back in 4 minutes. Okay, so next topic is total variation for image smoothing. So, let's say this is the original image, looks really clear, but typically you'll see something like this. And then you can choose to use this for your data set, or you can choose to smoothen it. And so the question is, how do you smoothen it? So this is after smoothing, TV smoothing. You see something that's more clear, and it's kind of removed the noise, basically, almost like magic. So total variation is a denoising technique, but it's also a smoothing technique. Do you see what is noise? Noise is there's a lack of smoothness, right? There's that graininess that's making it less smooth. So total variation is a denoising technique that's based on smoothing. It says, can you keep the image kind of smooth, make it flow smoothly from one side to the other, from left to right and from top to bottom? So you kind of looking at both directions and saying, can you make it more smooth? So that is total variation, right? You can say it's based on gradients. It's looking at gradients in the X direction and in the Y direction. So, oh, great. Actually, you know what? So yeah, you're usually given this as your input. It's noisy, and then total variation can denoise. And then you can see this looks close to the original image. Pretty good, right? You can take a noisy image and denoise it, make it look like what you had in the first place. So other examples, again, noisy image, total variation makes it smooth. Teddy bear, smoother teddy bear. Something even more crazy. This is blurred and noise. Like there's not just noise, there's also blurring. And you are able to apply certain kinds of total variation and reconstruct it. Obviously, there is some assumptions here, but with those assumptions, you can actually do some reconstruction that looks pretty good. So background for TV or total variation, it's based on the concept of regularization. How many of us are heard of the word regularization before from a previous class? Or 1, 2, okay. So regularization is a way of changing your loss function. We looked at loss functions before. It's adding something to your loss function so you can regularize the solution. You're guiding the solution in a particular direction. You're saying, well, I want to denoise the image, but like kind of make it smooth. So then I would add a regularizer, and make it do that. So it's kind of a way of thinking of guiding a solution towards a particular goal. And you guide it based on your objective. And you also guide it based on some existing functions that can help you with that. For instance, L1 and L2 are typical regularizers. L1 and L2 norm are typical regularizers that you might use for regularization. And total variation is specifically using L1 norm. It's using it really well and helping us with the denoising. And today we'll also discuss the intuition behind why it works, which is super important. But before we go into total variation, let's look at these norms and regularizers that can help us understand TV better. So the first norm is L1 norm. L1 norm of a vector is the sum of absolute values of the entries elements of the vector. So notice L1 norm is close to 1 transpose x, where 1 is the vector of ones and x is the vector x. It's close but not the same. Do you see why? So both L1 norm and 1 transpose x are summing up elements of x. The only difference is you're taking an absolute value for the L1 norm, right? And this is important. You see, for instance, if you were to do a least squares regression and you made a fit, right? So let's say, you might have looked at least squares regression in a different class or in your undergraduate program somewhere. And then you have, this is your line of best fit. So now these are the deviations, right? Here's a deviation 1, here's a deviation, here's a deviation, here's a deviation. So this is your prediction. And this is your actual value. And this is your deviation. So your line of best fit is going through most of your data points, which is great. Because if you had something like this, that would be the line of the worst fit. Because it's going through no points, right? None of the points. So line of best fit is doing a good job because it's going through the data. And it's also like lining up with the principal component 1. If you remember from the last lecture, we spoke about principal component being the direction of the maximum variance. So if someone were to ask you, can you take all the deviations and tell me what's the average deviation look like? You could do 2 things. The first thing is just take all the deviations, average them out. Would that be a good metric for computing the average deviation? No? If no, why? If yes, why? Anyone wants to share? Again, it's easier to consider examples, right? So let's say this is deviation is 5, this is -3, this is 4, this is, maybe this is -1. And basically someone asks you, can you tell me what the average deviation is from the line of best fit? And you say, well, take the sum divided by the number of points, and then that should give you the average deviation. There's something wrong with that. What happens if all the positives equal all the negatives? You get a deviation of 0. But is the deviation 0? No. The deviation does exist. So what that tells you is you cannot just add up all the deviations when you do a line of best fit, average it, and expect to get a sense of what the actual deviation is. So what's missing there is the absolute value, which is basically what the L1 norm is doing. So if you take the L1 norm of the deviations vector in the line of best fit, that is going to give you the sum of all the deviations, and then you divide it, you're going to get an average deviation that's non-zero, which is going to be close to what the actual deviation is, average deviation is. Maybe the average deviation is 3. So average deviation means you're going this way or this way by 3 most of the times. That's an average deviation. But just summing it up and divided by the number of points is going to give you 0. So this is an example application of L1 norm, right, that you see in practice. But L1 norm is also going to show up for total variation. Okay. All right. And then there's the L2 norm. L2 norm is something that we've seen before, right? Where have you seen it? We've seen it in Euclidean distance. By the way, L1 norm also shows up in Manhattan distance, because the whole idea is like if you have like streets, right, and then you want to say what's the distance between this and this, you'd say, okay, go this way and go this way. That's the distance. But L2 norm is going to say go this way. So L2 norm is just like looking straight, but L1 norm is like following the streets, right? So L1 norm is practical in certain settings. L2 norm is more practical when you can just go straight. Yeah. So obviously L2 norm is not a good metric for measuring the distance between 2 points in streets, right? But it might be a good metric for measuring distance in a desert, because you can just walk straight. Why do you have to go? There's no streets there. Yeah, so L2 norm would give you a better metric. So L2 norm is essentially the sum of the squares of the entries in a vector and then take a square root. All right, and notice that the L2 norm is less than L1 norm. Yeah, so can you see it here? The L2 norm is taking a faster route, whereas L1 norm is taking a longer route. So L2 norm is less than L1 norm. This is mathematically true. It's also true intuitively. You just saw a picture of that. Okay. So just to solidify our understanding of L1 and L2, which we'll be using it in total variation, let's look at an n-class exercise and apply the concepts of L1 and L2 norm and compute it. Okay, so I see a lot of force. That's great. So L1 norm is straightforward, right? Because you take the absolute value, sum it up, and that gives you 8. So that rules out the second and third option. Now it's between the first and the fourth option, and you get something like square root 22, which is closer to 5. Yeah, it's not closer to 4. Okay, great. So there is more deep theory behind how L1 and L2 norm play a role in different settings. So here's an example in the context of linear systems. Okay, so let's say you have a linear system, x theta equals y, right? So it's a linear system, it's a linear equation, and x is maybe your data matrix, theta is your parameters, and y is your output. There could be, let's say there's multiple solutions to the system, right? A linear system can, if it's underdetermined, has multiple infinitely many solutions. If it is if it's overdetermined, then you might have one solution or no solutions. So because of the way it is set up, it's a hyperplane, it's going to have multiple solutions, right? It is by definition going to be underdetermined. Yeah, otherwise you wouldn't have a hyperplane. Okay, so let's say you have the solution. The question is, what is a point on this line that has the least L1 norm? Okay. So the interesting thing about this is to understand what the L1 norm ball looks like. So I think maybe we should start with L2. So L2 norm ball is what? X squared plus y squared is less than or equal to 1. Let's use a better notation. X1 squared plus x2 squared less than or equal to 1. Yeah, do you guys agree? Or less than or equal to alpha, let's say. This is the alpha norm ball. So what does this look like? It looks like a circle. Yeah, you guys agree this is the equation of a circle. Yeah, x1 squared plus x2 squared is something. So, okay, so the L2, so you'd have something like this. This is alpha, this is something else, V2 alpha, whatever, and then you have something here. So this is like growing the ball. So when you have a smaller alpha, you have a smaller ball. And then as you increase the alpha, your ball grows. Does it make sense? So let's look at it here. When you have this hyperplane, maybe you start somewhere here. And then the question you're asking is, what would be the minimum alpha when you expand the ball, you hit the surface? Okay, so that is the least L2 norm solution to this system. Do you guys agree? You couldn't have something smaller because it doesn't fit. You would have, just when you hit it, that's when, so here I'm hitting it. So this is like the minimum alpha. So whatever this alpha is, that's the minimum alpha at which you hit the hyperplane. Yeah. Okay. Maybe there are other alphas, like I can expand it out this way. Okay, so this is a higher alpha. So this is not the minimum alpha. Yeah. So you notice the, you could also say this is like minimizing the vector x such that, oops. I think let's use a better notation, minimizing theta such that x theta equals y. So this is x theta equals y. This is a linear system. Find the minimum expansion of the ball such that you hit x theta equals y. That's what this figure is representing. Okay. Interestingly, when you go from L2 to L1, instead of having a ball, you have a diamond. And you're expanding the diamond. Okay. So let's look at that here. So what is the L1, right? L1 norm of 1 is this plus this. Yeah, that makes sense. And the L1 norm ball is this less than alpha. So that means x1 plus x2, an absolute value less than or equal to alpha. So this particular equation is giving you a diamond instead of a circle. Just going from squaring to just adding this absolute values, you can test it out. So let's say let's say this was x1 plus x2 less than or equal to 1. So less than means this whole shaded region, right? If it was equal, it would just be the boundary. It's less than or equal to, so it's a shaded region. What is this point here? Anyone? This is on the boundary. For this equation. So you know x2 is 0 at this point, right? At this point, x2 is 0. So what must x1 be? It must be 1 because alpha is 1. Yeah, so this is 1, 0. What is this point? This is 0, 1. What is this point? Minus 1, 0. Yeah. So notice it doesn't matter if it was a negative sign because you're taking the absolute value. Okay, and this is 0, negative 1. So these are the 4 defining points for the diamond for alpha equals 1. Yeah. So that's why it's a diamond. Like you can convince yourself that the L1 norm ball looks like a diamond. Okay. Now, why are we discussing circles and diamonds here? Because if we do the same thing as for the L2 norm and you expand this diamond, look where you're hitting the hyperplane. You're hitting it at a corner point. You're not hitting it somewhere in the middle. Okay. So this is where x2 is equal to 0, right? So if you were to minimize an L1 norm for a hyperplane, you're going to hit a point that has a lot of zeros. So that is why L1 norm is called sparsity inducing. It produces a lot of zeros. Okay. But L2 norm, as you can see, it hits somewhere. Oops. Sorry for that. So L2 norm is something that may not produce zeros because just the nature of, so this is visualizing and understanding in 2 dimensions, also applies in 3 dimensions, but you have to extrapolate it to multiple dimensions. And that's where you can see that L1 norm is going to produce a lot of zeros. It's sparsity, that's why it's called sparsity inducing. Okay, I think there's more on this here. We'll come back to it if needed. So L1 norm is helpful for sparsity. So it likes to produce a lot of zeros if you were to optimize for it, for that reason. Okay. So why is it helpful for image denoising? Well, the sparsity property can help denoise an image because when you look at the difference between 2 pixels, consecutive pixels, For a smooth image, you want the difference to be 0. Yeah. If it's noisy, then you'll have up and down movements, and that's not going to be 0. So if your image is noisy and you want to denoise it, essentially you're saying, if nothing much is changing, let's say you have that image of a face of a person. Let's say you're on the face. Well, as I go from one point in the face to the other point, maybe not much is changing. So keep it similar. Don't kind of make it up and down. So that means you want the difference to be sparse, the difference of consecutive or adjacent pixels to be sparse. So if I apply L1 norm to the difference or the gradient of the pixels in the image, that would be a way to make the image smooth. Do you guys agree? Does it make sense? So that is why we would be using L1 norm for gradients in an image. So let's look at gradients in an image. So what does a gradient look like? So this is the horizontal gradient. So we represent it by dx because it's horizontal. So let's say we have an image here. So you take this row and then you take this row. So this is I plus 1. And let's say this is j. So I'm looking at these 2 points here. And this is I plus 1j. This is ij. Okay. So these are 2 adjacent pixels, yeah? So when I go in the horizontal direction, when I'm looking at horizontal pixels, I want the adjacent pixels to be smooth as much as possible, right? So I want this difference to be close to 0. And L1 norm can help us with that as a regularizer, yeah? And the same thing holds true for vertical gradients. So vertical gradient is the reverse of this. You take an image, and then this is j, and this is your j plus 1. And then you have an I here. So this is ij, this is ij plus 1. Okay. And I'm basically saying the difference between ij plus 1 and ij, as much as possible, keep it 0. But if there are edges, there are changes happening, okay, then keep it non-zero. So that will ensure, again, the image is smooth in this direction. So dx and dy make sure the image is smooth in vertical direction and the horizontal direction. Yeah. So the total variation is taking all of this, combining it as an optimization problem and saying, find me an image that is close to the denoised image, a noisy image that you started with, but make it smooth. Okay. So the way we would do it is to solve an optimization problem. So there's a lot of things going on here, but let's make it simpler. So let's say you have an image I. So let's say this is a noisy image. Okay. And let's say you have I hat. This is a denoised image. So how do I denoise an image? Okay. What I would do is I would want to pick an image from all possible images such that I'm close to the original image. Yeah. So this is saying stay close. Don't deviate too much from the noisy image. Because if I just change it randomly, then what's the point? I want it to stay close, but I want it to be smooth. So this is saying stay close, but this is not enough. So then you say, well, make it smooth. So you know what I is, you don't know what I hat is. Look at all possible I hats that you can, look at all the possible candidates for I hat, but pick the one that minimizes the sum of this quantity and this quantity. But there's going to be a trade-off parameter. There'll be some lambda here. As you change lambda, you're going to make the image more and more smooth, but you might start deviating from your noisy image. So you don't want that to happen. But if lambda is 0, what's the solution here? If lambda is 0? If lambda is 0, this quantity is going to be at least 0, and it's going to be 0 when I hat is I. So that means if lambda is 0, you didn't do any denoising. Just return the original image. So we don't want lambda to be 0. We don't want it to be at least some positive value, but you have to pick some value where you have a good trade-off between these two, right? So that is something that you can experiment with in assignment 2 that we have, is to see what is a good lambda value where you get a good trade-off between staying close to the noisy image, but also denoising it, making it smooth. Okay, so this total variation, this TV of I hat, it's a function that's also called, that's also a regularizer. And this regularizer is based on the L1 norm, okay, which we covered just now. So there's like two versions of TV. One is an isotropic TV and there's an isotropic TV. These are just minor variations, but both of them use L1 norm. So you remember dx? Dx is the gradient when you go from one row to the other, like how things change from one row to the other. And dy is when you go from one column to the other. Yeah. So you're saying, let the gradient, this is saying, when I minimize the L1 norm here, I'm saying keep gradients in X and Y direction sparse. So make minimal changes. Don't make too many changes from one pixel to the other. That keeps it smooth, right? So that's what TV is doing. It's applying an L1 norm to the gradients. Yeah. And then there's isotropic TV, which is kind of close to the anisotropic TV, where you are applying an L1 norm, but you're also applying an L2 norm inside. So it's a small variation on that, right? So here are some results. Here's the original image. Here's the noisy image. Here's the anisotropic TV denoising, and then there's isotropic TV denoising. You can see both of them are smooth. So making the gradient sparse does help in making the image smoother and denoising, right? But there could be some minor differences between anisotropic and isotropic. But the key thing is that you're using TV in both scenarios. Here's another example where you're denoising an MRA image. I don't think we see the noisy image here, but the noisy image might be close to this, something like this. And then these are the smooth inversions. Okay. Yeah, I want to stop here and ask if you guys have any questions on total variation, the math behind it, the intuition behind it. So there's like 3-4 different pieces that we covered here. Is there a mathematical way to find the best lambda? Yeah. For supervised learning problems, you can do hyperparameter tuning. So lambda here is like a hyperparameter. So we have a lambda here, sorry, lambda, and lambda. Yeah. So for supervised learning problems, you can do hyperparameter tuning. So lambda here is a hyperparameter. So this is hyperparameter, and U is a parameter. So we're differentiating parameters from hyperparameters. Parameters are something that you directly optimize. You search for parameter. You want to optimize and say, here parameter actually represents maybe an image or a representation of an image. So you want to search for a better image, a smoother image. So that's a parameter. Hyperparameter is something that is a setting in your optimization that can do some kind of a trade-off. If you change the setting, you get a different output. Okay. So for supervised learning problems, you can do hyperparameter tuning based on some held out data set, like validation data set. But this is unsupervised. We don't have any supervision. So you would have to do some kind of manual search and do manual validation. So we don't have an automated way to know where you stand. So you might have to experiment with and see how the image looks like because it's unsupervised learning. Does that make sense? So we will cover a little bit more on this, but hopefully, you're able to see how applying an L1 norm on gradients makes it sparse. And because it's sparse, the pixels are not changing from one location to the other. And because they're not changing from one location to the other, you get, where is that image? Oh, it's here. You get a smoother image. Yeah. So this, if you see here, if you go from here to here, there is noise, right? There's noise everywhere. So the gradients for this image is not sparse. The gradients here are sparse. So sparse means fewer changes in the gradients or a lot of zeros in the gradients. So you can think of it either way. I'm sorry about that. Any other questions? So this is, the L1 norm regularization. It's a very deep topic. So even if, some of it is not clear, don't worry about it. We'll cover it again in the next lecture. But again, we've covered a lot in a short lecture. So if some things are not clear here, that's totally fine. But main thing I would focus on is intuition behind it. What's the intuition behind using TV? Why are we doing TV? How is it helping? What is this optimization problem and why is it giving us a smooth image? So if you're able to understand this at a high level, then you can always fill in the details a little bit later as well, right? So I would focus on that, start there, and then if you have any missing details, we can discuss in office hours. We'll also go through it again in the next lecture. Anything else, guys? Okay. If nothing else, stop the recording and we're good for today. And hopefully, I think you have all the material needed for assignment 2. And just have fun with assignment 2. It's a nice assignment, has TV and video chaining in it. So you'll have fun uploading a video to YouTube and sharing it on Discord. So yeah, for the video part, what I would say is pick an image set. You can pick any set of images from the web, but pick a set of images where you have good amount of clusters. Like let's say flowers, you have roses, jasmine, whatever, and you have enough roses, enough jasmines. So when you actually chain it into a video, it looks like there is some content there. Otherwise it'll just like go like that and you won't even know what happened. Okay. So you may want a sufficient number of images and sufficient number of clusters or images per cluster so that you can have this nice transition from one image to another as a video. Okay. All right. Okay, so we're good for today. I'm stopping the recording and I'll hang around for a couple of minutes if you have any other questions you want to ask.